Welcome! In this video, I'll show you how to solve problem 2.40 as it appears in the third edition of Griffiths' Introduction to Quantum Mechanics. Now, this problem states the following. It says, in problem 2.22, you analyzed the stationary Gaussian free particle wave packet. Now, solve the same problem, but for the traveling Gaussian wave packet, starting with the initial wave function that we have right here. A e to the minus ax squared times e to the I Lx, where L is a real constant. Now, part A asks us to normalize the wave function. Then B is, I took these, by the way, from 2.22. It isn't explicitly written in 2.40, but this is what they mean. B is to find the wave function itself as a function of time, right? Because this is the initial wave function, right? Then we need to find the modulus squared of our wave function. And then we need to use that to find the expectation values of x, p, x squared, p squared, and the uncertainties sigma x and sigma p. And with that, we can check if the uncertainty principle holds or not. Okay, so what is the procedure? Because this will be a long and very tedious problem. So we need to take a breather and map out what we want to do. So first, of course, we will normalize. But once we have the normalized wave function, how do we find the wave itself? Well, we know from what we saw when we were discussing the free particle that the wave function as a function of time is given by 1 over the square root of 2 over pi. And then we integrate over all of k, right? Every value of k of f of k times e to the I kx minus omega t dk, right? This is, of course, for this wave packet. But we don't have phi of k. So in order to use this, we first need to find phi of k. And the formula that we found for this previously is 1 over the square root of 2 pi integral from minus infinity to infinity. It's very similar of the initial wave function, which is what we do have, and then e to the minus I kx dx. Okay, so this is as a reminder, right? This is a reminder. And when we have this written out, then our path ahead is pretty simple. First, we calculate this, and then we plug it in there. And with that, we can easily determine the modulus squared, which we can then use to find everything else. Okay, so that is our plan. Now let's begin with step 1, normalizing the wave function. Thus, part A. So 1 is going to be equal over the integral over all of space of a squared. And what is our wave again? It is e to the minus 2ax squared, and then we got e to the I Lx times e to the minus I Lx dx. So in this case, as we can see, the complex part cancel out, and we end up with exactly the same thing that we had in problem 2.22. So we get a squared times this Gaussian integral, e minus 2ax squared. And this, as we have seen a few times, is the square root of pi over 2a. If you are unsure where this came from, this right here is an integral that cannot be solved by traditional means. You have to solve it numerically. And this is called the Gaussian integral. You are going to encounter it very often, very often. And its result in general, so the integral, if you find something that is from minus infinity to infinity of e to the minus bx squared dx, this is the square root of pi over b. Okay? This is an integral that we will encounter very often. All right. Let's continue then. So with this, we can find a squared quite easily, right? We simply multiply, so a squared is going to be square root of 2a over pi, and thus a is 2a over pi to the 1/4 power. So there we go, that is part A. Now part B asks us to find the wave function as a function of time. As I mentioned, in order to do that, we first need to find this phi of k. So phi of k, part B, this is 1 over the square root of 2 pi. But now let's plug in the wave function. So we plug in a, which we know is 2a divided by pi to the 1/4 power. And then we get integral from minus infinity to infinity of e to the minus ax, e to the ilx, and I don't remember anything else. Then comes, that is the wave function. Whoops. That is the wave function, right? Yes, minus, oh, good thing I checked. Okay. EILX, and finally, we need the minus IKX. All right. Now, this is basically the same thing that we had in the problem 2.22, which I also have in my channel in case you want to check it out. But this time we have this additional exponential right here. So we are going to do the exact same procedure that we used in 2.22. And I do recommend that maybe you solve that problem first. I'm going to explain everything anyways. But that was basically an easier version of the same problem. So if you are maybe struggling, it might be a good idea to check that one out first. I'll put the link in the description. Okay, so the way to solve this is we want to transform this into a Gaussian integral, right? We want to have inside of the integral something that is e to the minus and then some constant, I don't know, alpha, times the variable squared. So to do that, we want to complete the square. So first of all, let's just put everything into one single exponent. So just like this, right? Just this plus this minus that. And now we can factor out x. So x, here we factor it out. Okay. Now, let's just take a look at the exponent here. And so the exponent, that is minus ax squared. Let's factor out minus a. So let's factor out minus a from this entire thing. We get minus a factor of x squared. And then we get a minus here. So we can either write it as plus and switch these signs in here times x. And we have to divide this by a. Okay. And now we want to complete the square here. So to do that, I'm going to go step by step here, completing the square. Now this means that we want to have something like x and then plus ik minus il. You could factor out the I guess. And then divide it by 2 times a squared. But this is of course not the same, because if we multiply through, right, and this is a good way, sometimes if you are unsure how to complete the square, you just write it like this and now multiply through. So we get x squared, then 2 times this times x, so plus ik minus il divided by a, and now this thing squared. So minus no, not the I, so we get k minus l squared divided by, and here instead of 2a we have 4a squared. So notice that we have this additional term here. So in order for this to be the same, we need to add this, so that when we multiply through, this thing cancels out and we are not doing anything illegal. Okay, so that is a nice way of working with this. And now we multiply through by minus a, basically to isolate this. Why? Because this thing right here has no x. So because it has no x, we are going to be able to take it out of the integral. I'll show you that in a moment. So we have minus a times x plus, I'm going to factor out the I now, I guess, k minus L over 2a squared, and then we get minus the other term multiplied by a, so we get k minus L squared over 4a. So this is the new exponent. Our exponent went from that thing to what we have right here. So let's see. Now, here there are a few changes, but I guess we can leave it like this for now. So we could try to combine some terms, but I don't think it's going to get much prettier. So leaving it like this is okay. Okay. And then we go into the integral minus infinity to infinity e to the, and now minus a x plus I k minus L divided by 2a squared. And then we have e to the minus, right? We can separate this into two exponentials. K minus L squared over 4a dx. And now notice that we can simply take this exponent out of the integral. So we get all of our constants in the front. And now this is a constant as well, e to the minus k minus L squared over 4a. And notice that in problem 2.22, we also got to this expression instead that before we had k, and then now we have k minus L. And now inside of the integral, we have this exponent here, but we can use a change of variables. We can say, all right, let u be x plus I k minus L squared divided by 2a. No, sorry, the squared is outside. That's my bad. Just like that. And that means that du is simply dx. So our exponent will now be e to the minus a times u squared and du. And this right here is a Gaussian integral. Once again, I told you it was going to come up very often. So we know what result that has. I'm just going to copy this. E to the minus k minus L squared over 4a. And now, square root of pi over a. Okay. So here, this pi cancels out this pi right here. And then notice that we have 2 to the 1/4, 2 to the 1/2, pi to the 1/2, to the 1/4, and a to the 1/4 divided to the a to the 1/2. So when we combine all of those, we get 2, we get a and pi, all of them in the denominator, to the 1/4 times the exponent, e to the minus k minus L squared divided by 4a. Okay, did I consider everything? So this and this, this and that, and that, this and that, yes. So this is our phi of k. So now we can simply take this psi and plug in our phi. So let's plug that in and find the wave function as a function of time. So this will be 1 over the square root of 2 pi, just using the formula that we wrote above, minus infinity to infinity, and then comes phi of k. Now, what was phi of k? It was 1 over 2a pi. So 1 over 2a pi to the 1/4, then e to the minus k minus L squared divided by 4a, and then we still have to add this other exponent, so e to the I kx minus omega t. So e to the I kx minus omega t. But what is omega? Omega, in this case, is h bar times k squared divided by 2m. And of course, multiplied by t. All right, I'm just going to double check. Yes. And dk. So what we want to do here is the same that we did in the previous integral. So as you might notice, here we are integrating over k, and the only place where k appears is in the exponent, both as k and as k squared. So for that reason, we want to complete the square, right? Take whatever is a constant, take it out, and then complete the square to turn this into a Gaussian integral. So that is the plan. But for that, we need to work a little bit with our exponent. So the exponent is going to be, now let's just expand this. So we get minus k squared plus 2kl minus l squared, all of that divided by 4a. Then what do we have? Then we get plus ikx minus I h bar k squared divided by 2mt. Okay, so that is the exponent. Now our goal is to isolate k squared to turn this into a Gaussian integral. But Gaussian integrals are of the form minus something, right? So we need to isolate a minus sign as well. So this will be minus, and now everything else. So k squared, or actually maybe let's do it here so I don't have to rewrite it. So this is a minus, this is plus, now this is minus, this is plus, this is minus, this is plus. Okay, so now let's factor out k squared. So we have 1 over 4a from the first term, and then we have plus I h bar t divided by 2m. And then let's factor out k. So plus k. What is multiplied by k? We have negative 2kl divided by 4a and negative ix. Oh, sorry, I included this twice, so only 2l, of course. And ix. Okay. And then we have yet another group, which are these things that don't have k, the constants. So that would be plus the constant is L squared. There we go. The constant is L squared over 4a. So that is our exponent. Now, what we want to do is combine these two expressions in order to, have to complete the square. These two have to become just one square and some extra residue that will be a constant. So to do that, let's, as before, isolate our k squared. So, just continuing down here, let's isolate k squared. So we get k squared, and basically by doing that, let's factor out the thing that is accompanying the k squared. So let me write it first. So 1 over 4a plus I h bar t divided by 2m. So this will be multiplying k squared and also this thing right here, but that thing doesn't have it, right? It doesn't have 1 over 4a plus I h bar t divided by 2m. So we need to multiply it and divide by it. So when we factor it out, it is only being divided. So what we are left with is k times minus 2l minus ix. This thing is divided by 4a. And now we need to multiply this by 1 over 4a plus I h bar t over 2m, but to the minus 1, right? So we are dividing by that. But I don't want to write it down here because it's too chaotic. And then finally, we still have our constant terms that are here, this minus L squared 4a. Okay, so this thing looks a little bit nasty, but let's not worry too much for now. So what we want to do, what we want to get to is something that is k I guess we can factor out this minus sign now. So minus, and this is now plus. So we get k minus 2l plus ix, and divided by 4a times this other thing, 1 over 4a plus I h bar t divided by 2m. And this is to the minus 1, of course. But what we want to do, right, since we are completing the square, this thing is twice this. So we need to multiply by 1/2. And this thing has to be squared. But of course, we need to compensate the fact that we squared this, and we need to now subtract this part squared, right? Because when we multiply through, we are going to have an additional term, and we need to make up for that. So by squaring, we get 1 over 4, 2l over 4a plus ix, and then 1 over 4a plus I h bar t divided by 2m to the minus 2, and this is squared. So that is the result of just completing the square, right? So this thing now turned into this. And of course, all of this is being multiplied by what we factored out before. So let's now write it out explicitly. So we get minus, now we have 1 over 4a plus I h bar t divided by 2m. And now let's multiply this with this thing here. So k minus 1/2 2l plus ix divided by 4a. And then 1 over 4a plus I h bar t divided by 2m to the minus 1, and this thing squared. So this is the part that depends on k. Now comes everything that is a constant, which is this part and this part. But we cannot forget that this is also being multiplied by the first term here. So the minus goes to a plus, and then we have 1 over 4. And this part is the same as what we have here. So it goes from to the minus 2 power just to the minus 1. So we get 2l divided by 4a plus ix squared. I guess we can write this. I was keeping it this way in case that it seemed to be that at some point we might be wanting to factor out 1 over 4a or something, but it doesn't look like it. And divide by 1 over 4a plus I h bar t divided by 2m. Okay, so this is our exponent. Now you see why we wished to work this algebraically outside of this expression, because it's just too ugly otherwise. Okay, so now notice that this expression does appear quite often, this thing right here. So maybe let's rewrite it and see what we can do with it. So if we just add this together with the minimum common denominator, we get, let's see, m here plus 4, actually we only need to multiply by 2, so 2I a h bar t divided by 4am. But here, of course, we can now divide by m. And when we do that, we get, I'm going to write this a little bit further up. So 2I a h bar t divided by m. And this m and this m simplify. So 1, and we don't have to write anything there. And now, this is, of course, going to be the same as here, by the way, right? And the same as here. Now here we can define a new variable so that this thing becomes cleaner. I will use the same notation as Griffiths, so I'll define theta as 2a h bar t over m. So plugging theta in here, we get 1 plus I theta. And now we can simply rewrite this up here. So this is 1 plus I theta, and this is minus 1 over 4a. And the same thing we do up here, where we also have this. So this is simply 1 plus I theta, and this is 1 over 4a. But 1 over 4 divided by 1 over 4a is simply a. Okay. And we don't need to bother doing anything here, because since this is in the exponent, we simply say, all right, let's use a change of variables. U is equal to all of this. So k minus blah, 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 right? This huge thing. And since we are going to take the differential du, and there is no k anywhere in these parentheses, this is simply dk. So that is very, very nice. Now, the exponential was this thing, and we just found what is in this part, right? We just found that. But we cannot forget that we still need to include this, okay? So we have to be very careful. Don't forget about it. All right, so with that in mind, let's now plug everything into our integral. So our constants go up front here, 1 over 2a pi to the 1/4 power, and then first we have this constant. Of course, the order doesn't matter, but we have that constant. So we get e to the minus L squared divided by 4a, right? Minus because of this minus over there. Don't forget about it. Then we have this expression down here. Now, this here is our constant. And that comes in here. So there's a minus sign in front that we cannot forget about. So this is going to be e to the minus a L over 2a plus ix squared divided by 1 plus I theta. Okay, so those are our constants. And then we have to plug in this thing into our integral. So it's going to be integral from minus infinity to infinity of e to the minus 1 over 4a times 1 plus I theta times u squared du. Now I'm just going to double check because I don't want to make any dumb mistake at this point. Yeah, that's correct. Okay, so this integral is simple. It's a Gaussian integral. So that is the square root of pi divided by what was inside. By what was in front, I mean, right? We had e to the minus something times u squared. And this pi is divided by that something. And that was 1 over 4a. So we get 4 up here, 4 pi a, divided by 1 plus I theta. So there we go. This is the wave function. We still can probably simplify this a little bit. So let's see how we can do that exactly. And then comes the other constant, which is this thing right here. Basically a to that thing. So we get e to the a, maybe let's stick to white. So that it's the same color in this part. So e to the a L over 2a plus ix squared divided by 1 plus I theta. And then we get the integral of minus infinity to infinity of e to the minus 1 over 4a 1 plus I theta times u squared du. And this is simply a Gaussian integral, right? So the result is going to be square root of pi divided by this thing. So divided by 1 over 4a times 1 plus I theta. And let's plug it in. So let's get rid of the integral, write in this instead. So we get square root of 4 pi a divided by 1 plus I theta. Okay, so there's a little bit that we can simplify. So we can take the 4 out of the square root, right, as a 2. So maybe let's write it here. And then we have 2 divided by 2 to the 1/2 and 2 to the 1/4. So we will be left with, so we have basically 1 minus 1/2 minus 1/4. So this is the same as 4/4 minus 2/4 minus 1/4. So we're going to be left with 1/4. So we get 2 to the 1/4. What else? Then we have this pi that cancels out this pi. We already considered all the 2's. Okay, and then we have this square root of a and this. So we get a to the 1/4. And then we have a pi here to the 1/4. Okay, so that's that one. And then we have our beautiful exponents. So e to the minus L squared over 4a, e to the a, L over 2a plus I x squared divided by 1 plus I theta. And there we go. This is our, okay, I almost forgot about this final part, this. So times 1 over square root of 1 plus I theta. There we go. This is our wave function as a function of time. Whew, and that is quite similar to the other wave function. Of course, it has to be, if we take L equal to 0, we have to be able to get back to what we saw in 2.22. So maybe let's just put this in a green square so that we can easily find it later. So the next part in the problem, we finally found psi x comma t. Now we want to find its modulus squared. So let's get to it. We know how to do it. It isn't difficult. I mean, in principle, it is simple. Maybe it's not easy, but it is simple. So the modulus squared is going to be psi conjugate times psi. So these real constants, actually all of these real constants will simply, be squared. So we get, instead of to the 4th, we are going to get a square root. So 2a over pi square root. Then e to the minus, instead of L squared over 4, it's going to be L squared over 2a. And that's as far as we go in terms of, just our constants. And then we have e to the a times L over 2a plus ix squared over 1 plus I theta. And all of this divided by the square root of 1 plus I theta. But now we have to multiply by the conjugate parts, right? So we get e to the a L over 2a minus ix squared divided by 1 minus I theta divided by the square root of 1 minus I theta. Okay, so these square roots here are quite simple. This is simply going to be the sum. So basically we got 1 plus I theta times 1 minus I theta. So this is the square root of 1 minus I squared theta squared. So we get 1 plus theta squared. Okay. And in principle, this is already done, but of course we want something that is as simplified as possible. So for that reason, we now want to start working with the exponents. Now, so let's focus first on dealing with the part that has the i's, right? We can leave this constant b for now, and we will just add it at the end. So the exponents with I, basically these two, so this and that. So that would be a times, and now let's just expand this, so L squared over 4a squared, and then we get plus L I x divided by a minus x squared over 1 plus I theta plus, and now the second one, so a times L squared over 4a 4a squared minus 2ixl divided by 2a. So, well, it's the same. The 2's cancel out. And then finally, minus x squared again, divided by 1 minus I theta. All right, so of course we can factor out an a that is apparent. And in order for us to do anything, we need to be able to have the same denominator. So let's multiply by 1 minus I theta divided by 1 minus I theta on this side, and by 1 plus I theta divided by 1 plus I theta on that other side. Okay, so let's do that. And of course, factoring out a. So factor out a. Now, multiplying here. So of course, now the denominator is simply going to be 1 plus theta squared. So here we get L squared times 1. So L squared over 4a squared. Then we get minus L squared I theta divided by 4a squared. Okay, now second term. Plus Lix over a minus, but now we get I squared, so it turns into a plus, Lx theta divided by a. Now the x squared term minus x squared plus Ix squared theta. We want to be very careful now. Don't make a dumb algebraic mistake. Now the second bracket, so we get plus L squared over 4a squared plus L squared I theta 4a squared. Now the next one, so we get minus Ixl over a minus, but now we get I squared, so plus xl theta divided by a. And finally, we get minus x squared minus x squared I theta. And all of this is divided by 1 plus theta squared. Okay, so let's take a look at this. Now, there's quite a few things that cancel out. So this cancels out this. IXLA. Let's see. No, these two are up. These two are up. This cancels out this. And everything else adds up. So we get a factor of 2 times L squared over 4a squared. So 2 L squared over 4a, but that's simply going to be L squared over 2a squared. So we already considered this and this. Now we get plus 2 Lx theta over a, right? There we considered this and this. And finally, minus 2 times x squared. And all of this divided by 1 plus theta squared. Now, we want to try to simplify this further. And although it might not look like it, there is a way to do it. So let's now notice that we have x squared and x. And, you know, this is kind of looking like perhaps you could get some sort of, you could complete the square. So let's factor out everything that is accompanying the x squared. So we get minus 2 times x squared. And let's also do it here with the x. So we get minus L x theta over a. And everything else remains the same for now. L squared 2a squared divided by 1 plus theta squared. Okay, and now let's complete this square. So we get a minus 2, and now this would be x minus, this is twice what we have to write here, so Lx theta divided by 2a. Not Lx, of course, the x we already took out because we're completing the square, and this thing squared. But now, for this to be legal, right, we need to subtract L squared theta squared over 4a squared. And then everything else plus L squared over 2 a squared, and let's see. Yeah, there, and all of this divided by 1 plus theta squared. Okay, and what was the point of this, you might be wondering? Well, check it out. Now we have, well, a here, the same, minus 2 factor of x minus L theta to a, and this thing is squared, so this is squared. But now, let's multiply through, so this minus 2 and this, so we get plus L squared theta squared over, now it's 2a squared because we multiplied by this 2, and plus L squared 2a squared. So here we can now factor out L squared 2a squared. So we factor out L squared 2a squared. And what we get is 1, right, from here, plus theta squared from here. And all of this divided by 1 plus theta squared. And thus, what we get is this part, so minus 2a times x minus L theta divided by 2a squared. But then we have this other term, so that's going to be plus L squared over 2a, and that's it, right? Because, and this, of course, divided by 1 plus theta squared, but this is no longer divided by it. So this is indeed simpler than what we had before, right? We started out with this, and this is much better. So this is what we can now plug into our result right here. So instead of that horrible, terrible thing, we get, let's see, so square root of 2a pi, then 1 over square root of 1 plus theta squared. Then we have e to the minus L squared over 2a, right? This is the one that we didn't touch. And now comes our result. So we get e L squared over 2a. And take a look at that. E L squared over 2a. So these two cancel out. And then the rest is minus 2a times that thing. So e to the minus 2a, and I don't remember what it was, x minus L theta over 2a. X minus L theta over 2a squared divided by 1 plus theta squared. Now, if we take a new variable, right, we can define w as, let's see, because we have a square root of a over this other thing, so we can define square root of a over 1 plus theta squared, just to simplify our notation. And by doing that, this changes. So we get square root of 2 over pi times, and we simply have w, right? Much, much cleaner. And then e to the minus 2w squared, right? Because this and this a is the square of what we have here. And then x minus L theta over 2a squared. So there we go. This right here is the modulus squared of our wave function. So the idea wasn't difficult, right? It was a simple thing, but of course, a lot of algebra involved. So there we go. That is part B. Actually, it's part C even. Nice. So now we need to find the expectation values of x, p, x squared, and p squared. So let's get to it. But thankfully, we have already done a large chunk of the work here, because we know that, so let's begin part D. So the expectation value of x This is the integral from minus infinity to infinity of psi conjugate times, so basically this, right? Psi conjugate x psi dx. But since we can commute x and our wave functions, this is basically x and the modulus squared, right? What we just found. So for that reason, this integral is simply minus infinity to infinity of square root of 2 over pi w, which all those are constants, times x e to the minus 2w squared, and then x minus L theta over 2a squared dx, of course. And this integral, right, maybe to just make it a little bit clearer, we can do it like this. So y, let's use a new variable. Y is going to be x minus L theta over 2a. And thus, of course, dy is simply going to be dx. So by doing that, we can write this as integral. Well, let's put our constant. So square root of 2 over pi w, integral of minus infinity to infinity. Our boundaries are still the same. Now, instead of x, right, we can rewrite from here. If y is equal to that, then we can easily see that x is y plus L theta over 2a. So let's write this in here. So this would be y plus L theta over 2a, right? Yes. And e to the minus 2 omega squared y squared dy. So we have two integrals, which I will write separately so that you can see this as clearly as possible. So here we have integral 1, which is integral from minus infinity to infinity of y e to the minus 2w squared y squared dy. That's the first one. And then we have plus L theta divided by 2a times the integral of minus infinity to infinity of e to the minus 2w squared y squared dy. Now, these integrals are very, very simple to solve. Why? This one, that's an odd function over this even domain, right? It goes from minus infinity to infinity. It's a symmetric domain and an odd function. So the integral of this is 0. I've mentioned before a few times, it's so important to start recognizing when a function is odd or even when you're doing an integration, because it might be very, very useful, right? And the fact that there is this y here is what makes this odd and what causes it to be 0. So we only have to deal with the second one, but that is a Gaussian integral. So we already know its result. So this is w L theta 2a times the square root of pi divided by 2w squared. Okay, so here we can start simplifying. So pi, square root of 2, w, square root of w squared. And what is theta? So L over 2a. Theta we defined quite a while ago. Let me try to find it. Here it is 2a h bar t over m. So it is 2a h bar t over m. So the two a's cancel out and we're left with h bar L over m times t. Right, so this one, of course, the expectation value of x, we can see that it does indeed change with time, and it makes sense, of course, since this time our wave packet is moving, it's no longer stationary. And if L was 0, then we would see that we would be at 0. Our expectation value would be 0 because we are not moving at all. So that makes sense. Now, finding the expectation value of momentum is very simple because this is simply m and the derivative with respect to time of x. So let's take this thing right here, derive it with respect to time, and we get that the expectation value is h bar L over m times m. So simply h bar times L. Pretty simple. Now let's continue. So now the expectation value, maybe I'm gonna put it like this in case we need to find it later. So now the expectation value of x squared, we find it the same way. It's minus infinity to infinity of x squared times modulus squared of our wave function. So let's plug it in, right? The modulus squared of the wave function is this thing right here, which we also wrote down here. So it is square root of 2 over pi times w integral from minus infinity to infinity of x squared e to the minus 2w squared, and my memory is failing, x squared minus L theta over 2a. I'm gonna have to check. Is that it? Minus L theta 2a. Yes, that's it. Okay, and dx, of course. So here, just as before, we define, wait, it's not x squared, it's just x. Okay, there we go. So y is going to be x minus L theta over 2a, and thus x is y plus L theta over 2a. So let's rewrite this. So of course, constants go outside, 2 over pi w, and then integrate, and x squared is now y squared, which is x minus L theta over 2a squared. But you know, we can just write it out explicitly. Sorry, that's y. And x squared is going to be y plus L theta over 2a squared. But you know, we can just write it out explicitly right away as y squared plus 2 times L theta divided by 2a. But this time, of course, the 2's cancel out, and we also get, of course, our y. And finally, we get L squared theta squared over 4a squared. Okay, and then we have e to the minus 2w squared y squared dy. Okay, so this integral, right, will be 0 because it's exactly the same as before. It's an odd integral. It's an odd function in a symmetric interval. So for that reason, that one is 0 and we don't have to worry about it. We only have to worry about these two. Now let's write the constants in the front as usual and separate these two integrals so that we can attack them separately. So we have y squared e to the minus 2w squared y squared dy. And then we have this, which is L squared theta squared, which is a bunch of constants, and then the integral from minus infinity to infinity of e to the minus 2w squared y squared dy. Okay, so this integral is just simple. This is a Gaussian integral. So that one will be square root of pi over 2w squared. So that one is easy. What about this? So let's call it I. Now, this sort of integral we can transform into becoming Gaussian. So if we call this right there just beta, right, just some variable, then we can see that if we have e to the minus, or maybe let's put it to the side as a comment, so just as a comment. If we have e to the minus 2w squared y squared, and we just call this thing beta and let it, you know, be a variable, and we take the derivative with respect to beta of this, then we get minus y squared e to the minus beta y squared. So that means that y squared times e to the minus beta, blah, 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 is minus this derivative. So that is what we are going to do. We are going to rewrite what we have inside of the integral using that trick. And that is a very common trick that we use while working with this sort of integral. When we have like y squared and then a Gaussian, right? We can use this trick. And you can use it too when it's like y to the fourth or something like that. So this integral is now minus the derivative with respect to beta. We can take it out of the integral because beta does not depend on y. And e to the minus, I'm going to just write it as beta for now to make sure that we don't get confused when integrating later. And dy. And now this is a Gaussian, right? This is a Gaussian integral. So we get minus derivative with respect to beta of square root of pi over beta, right? And we can, for clarity, just make sure that this is very, very clear. We can write this as minus square root of pi times the derivative with respect to beta of beta to the minus 1/2. So this is 1/2, right? Because we get minus 1/2 times minus 1. So we get positive 1/2 square root of pi, and then beta to the minus 3/2. But what was beta? Beta was 2w squared. So this is to the minus 3/2. So that is the result of that integral. So let's plug it back in here. So that thing is square root of pi over 2 times 1 over 2w squared to the 3/2 power. Okay, so there we go. And now let's see what we can simplify. So square root of pi, square root of pi, square root of pi. And then we have square root of 2, which we can factor out and cancel with this. And here we go from 2 to the 3/2 to just 2, right? And with that, we can also factor out a 1/4. So let's not confuse anyone. So let's see, we have 1/4 that comes from factoring out this, this, and this. So we factor all those out. Then we have this w. If you notice here, this w squared, we have to take the square root. So we get w, and then we cube it. And then we multiply by this. So we basically get, in the first term, 1/w squared. So all we have left for the second term is L squared, theta squared, and divided by a squared, which, you know, don't miss it. It's still there. Okay. So now we just multiply through. So the first part is 1/4w squared plus L squared over a squared, and now, well, over 4. And now let's put in the value for theta squared. So theta was 2h bar a t divided by m. So we get 4h bar squared t squared a squared divided by m squared. So from here, the first part remains the same. But then the a squares and the 4's cancel out. So we get L squared h bar squared divided by m squared t squared. And this part, by the way, is what we can interpret as the velocity of the particle. So finally, what we have to find is the expectation value of the momentum. So let's just go down here, I guess. This is minus h bar squared times the integral from minus infinity to infinity of psi conjugate times, and now comes the reason why this is not quite simple, because we have to take the second derivative of our wave function. Now, what was our wave function? I have it written down right here. So we need to calculate that second derivative. So of course, we need to calculate the first one. So this is the derivative with respect to x of, let's see, 2a over pi to the 1/4 times, well, this is a bunch of constants, so 1 plus I theta. Then we have e to the minus L squared over 4a. And now comes the relevant part, so that's e to the a ix plus L over 2a squared divided by 1 plus I theta. Okay, so we have to take the derivative of this. Now, this entire thing here, that's all of this, including this exponent, that's never going to change, right? That doesn't depend on x. So let's just call it gamma or something, because I don't want to have to write it down all the time. So the derivative is gamma times, and now this is simply an exponential. So by the chain rule, we get 2a times ix plus L divided by 2a. We have to divide by 1 plus I theta. And because of the chain rule, we multiply by the derivative of what is inside. So we get 2ai times, of course, still the same exponent. So ix plus L divided by 2a squared 1 plus I theta. And this is, look at this, gamma times this exponent is our wave function. So this is 2ai times ix plus L over 2a divided by 1 plus I theta. And this is what came out from the derivative, and everything else is our wave function. So that is the result from taking one derivative. So now let's take another. So taking the second derivative, now we have to use the product rule, right? First, we take the derivative of this and we multiply by the wave function. Then we take the derivative of the wave function and we multiply by this. So the first part, we get, the only thing that depends on x is this. So we get 2ai divided by 1 plus I theta, and in the parentheses, we get I, right? This part doesn't depend on x, so its derivative is 0. So we get I squared, so, just minus. And this, of course, times our wave function. And then plus this thing times the derivative of the wave function. But what is the derivative of the wave function? It is this again. So we get 2ai ix plus L over 2a, and this is divided by this, and all of this is squared times psi. Thus, let's plug this in to our expression for p squared. So by doing this, we get minus h bar squared of the integral from minus infinity to infinity of, and now psi conjugate times all of this. So we are going to get several different parts. So first we get minus 2a, 1 plus I theta, and psi conjugate times psi is our probability density squared. Now the second integral, this I will be a minus, so we get minus 4a squared divided by 1 plus I theta squared, and everything else has to stay inside. So then we have the integral from minus infinity to infinity. And here, let's see, we have this parentheses squared, which gives us minus x squared plus ixl divided by a plus L squared divided by 4a squared. And this multiplied by psi conjugate psi, which is the probability density squared. Okay. Now, let's continue. Here we can take out the constants, and we are left with the integral from minus infinity to infinity of the probability density squared, right, dx. But what is this? What is this? We are asking, what is the probability of finding a particle anywhere in space? That is 1. Our wave function is normalized, so this thing is 1. And then we have the other integral. And here we have three parts, of course. The first one is minus integral from minus infinity to infinity of x squared psi squared dx. What is that? That is simply the expectation value of x squared. And that is something that we have already calculated. So let me plug in the value that we found. So that value is 1 over 4w squared plus, but a minus because it's already in front, h bar L t over m squared. But we know that the velocity of the group is hl over m, so we can simplify this by writing it as v times t. You don't have to do this, but it makes algebra simpler. You could perfectly well just do everything the way it was, leave it the way it was, but it's going to be a bit messier. Okay, so now this is the first part. Now let's continue with the second integral. So here we get IL over A times the integral from minus infinity to infinity of x psi squared dx. But once again, we already found that. That is the expectation value of x. And what we found as a result for that part is that it is v times t, right? H bar L over m times t. And finally, this third part is L squared divided by 4a squared integral from minus infinity to infinity of psi squared dx, which is 1. Our wave function is normalized. So there we go. Now there's still more that we can do, because in principle this is the solution, but we can simplify this. So let's factor out the negative signs. Let's factor out 2a. So when we do that, we get 2a h bar squared, and then what we can do is take common denominator for these two, which is of course 1 plus I theta squared. So we get 1 plus I theta minus 4a, no, not 4a squared, so we factor it out, so 2a. And this is divided by 1 plus I theta squared. And this 2a is multiplying our parentheses. But what can we do here? Well, first of all, we can remember what w was defined as. So w, we had defined it as the square root of a over 1 plus theta squared, right? That's what we had defined it as in the beginning of this entire thing. So for that reason, w squared, which is inside of this, is going to be, so this is minus 1 over 4, so 1 over 4 times 1 plus theta squared, and all of this is divided by a. Now, what about this? Notice that we have minus v squared t squared, so this is basically I squared, right, plus I squared, and here we have I vt times 2 basically, because there's a 4 here, right, and L squared a squared, which is also here, but not squared. So what I'm hinting at is that this looks like it is a perfect square. So let's try it out. So IVT plus L over 2a squared. So the first part is minus v squared t squared, right there. Then the cross product is IVTL over a. IVT, there it is. And finally, L squared over 4a squared. So we can write it like that. Okay, this is looking much, much better. However, we can still, do quite a few things. For example, in this parentheses, let's just add everything together. So take common denominator, we get 2a IVT plus L divided by 2a. But what was v? Right? V we had defined as h bar L over m. So, let's just write it in here, maybe like this. So this is h bar L over M. So h bar L and I don't know, M to the minus 1. Okay. And what is this? Now, theta we had defined as 2a h bar times t divided by m. Let me double check that I did 2h bar at divided by m. Yes. So if we take this, 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 and this, we get theta, right? So we can now rewrite what is inside here. So this is I theta L plus L divided by 2a. But we can now factor out the 2a and the L. We can write this as L squared divided by 4a squared, factor of 1 plus I theta squared. Okay, now it's slowly looking like it makes some sense. Another thing that we can do with the objective of trying to get rid of at least some of this is to rewrite 1 plus theta squared as 1 plus I theta times 1 minus I theta. So this thing right here, we can rewrite as 1 plus I theta, 1 minus I theta. And now we are finally in the position to make some real progress, because we have 1 plus I theta here, 1 plus I theta here, and 1 plus I theta here. So we can cancel out one of these with this, which is now 1, with this, and with that. So now rewriting all of this, we get 2a h bar squared, and then 1 plus, well, let's actually take this outside as well, the denominator. So we get 1 plus 2a factor of, and now we have minus 1 minus I theta divided by 4a plus L squared divided by 4a squared, 1 plus I theta. So that is 2a h bar squared, 1 plus I theta, and then we get 1, and now multiplying through, we get minus 1 minus I theta divided by 2 plus L squared divided by 2a, 1 plus I theta. And now we can multiply by 2 so that we get rid of these divided by 2's. And this thing here turns into a 2. And now notice we have minus 1 plus this thing. 2 minus 1 is simply plus 1. And now we have 1 plus I theta here, 1 plus I theta there. So this is a h bar squared, 1 plus I theta. And then we have 1 plus I theta, factor of 1 plus L squared over a. So this cancels out with this. We can multiply through with a, and we have h bar squared factor of a plus L squared. And there we go. This is the expectation value of the momentum squared. So now if we want to find the uncertainties, sigma x, for example, this is the square root of what? Of x squared minus x squared. So let's plug in our values. So what were they? Let's see. It was 1 over 4w squared plus, then we had h l t m squared. So this was the expectation value of L squared. And then the expectation value of x was h bar L t over m, and we have to square it. So sigma x is simply 1 over 2w. There we go. Now sigma p, of course, the same way. So p squared minus p squared. And what were our results? So p squared we have right here. That is h bar squared a plus l squared. And p, let me double check. Where did we have p? P was h bar l. So minus h bar squared l squared. So this and this cancel out, and we get h bar square root of a. So the uncertainty principle, sigma x, sigma p, this gives us 1 over 2w times h bar square root of a. And what was w? W was, let's see, so this is h bar times square root of a over 2, and w was square root of a divided by, what was it? I'm going to double check. I don't want to make a mistake at this point of the video. So it is 1 plus theta squared. And theta squared, so this is h bar a divided by 2, 1 over square root of 1 plus, this would be 4 h bar squared a squared t squared m squared. So there we go. We can't really go too much closer than this. But, well, as we see, the uncertainty principle does still hold. So this is actually the same as in problem 2.22. So there we go. The uncertainty principle still holds. Now, the problem was relatively long, but as I mentioned, it isn't really complex. It is simply annoying, a lot of algebra, a lot of, just integrating everywhere. But the procedure itself is relatively simple. So I hope this was useful to you. If it was, please do make sure to leave a like on the video, comment, and subscribe. And if you really like my content, maybe consider supporting me on my Patreon. That really allows me to dedicate more time to making videos such as this. So I'll see you in the next video. Thank you very much for watching.